In this video, I'll explain about composition of functions. If you have two functions, you can combine two functions to get a new function. That is what called as composition of functions. So mathematically, it is defined as if you have a function f from a to b and g is a function from b to c. These are two functions. Then composition of f and g is denoted as g composite f. It is a function from a to c. G composite f means f first, g next. So a to b, then b to c. It is like transitivity. It is a function from a to c given by g composite f of x is equal to g of f of x for all x belongs to a. So pictorially, this using the arrow diagram, I had represented here. F is a function from a to b and g is a function from b to c. Now this f is taking an element of a to an element of b, which is f of x. F is taking x to f of x. Now g is taking element of b, that is f of x, to a new element which is in c. So g takes f of x to a new element, g of f of x. So this is how the element looks like in the set C. Now G composite F is nothing but it is a function from A to C, where this G composite F takes x to g of f of x. It is like transitivity. This is a mediator. Now B is a mediator. Now x goes to g of f of x. So combining two functions, I have f, I have g. These are the two functions. By combining these two functions, I will get a new function, that is g composite f. Its input is x and output will be of the form g of f of x. So that is what the meaning of composition of two functions. Similarly, you can define f composite g also. G first, this comes first and f comes next. So f composite g of x is equal to f of g of x. See, all these definitions are possible, all these connections are possible if you have, in the first case, f is taking 8, f is a function from a to b, g is a function from b to c, means there is a connection. If there is no connection from here to the next set, then we can't establish composition of two functions. So to define composition, this is what the requirement is. Range of g should be domain of is a subset of domain of f. This is in the case of f composite g. I have defined g composite f because while taking the function g itself, I have taken it from b to c. So a to b, b to c. There is a continuation for transitivity. So this acts like a mediator, and I can proceed further because of this. So in case you need not have, if you take g first, g goes to b to c, then it is from a to b. C to b, it is not there. B to c, then usually as per the definition, it should, you may think like it should go from c to b, but though it may not go from c to another set, this condition, range of g, means whatever the output you will get after taking elements of b to a new elements of c, then that is called as a range. That range should be subset of domain of f. If it is a subset of domain, subset in the sense it can be contained in the domain of f, or it can be equal to the domain of f, in that case only you can define f composite g. Otherwise the composition of functions can't be defined. The second note is that if G composite F is defined, F composite G need not be defined. So there is no guarantee that if G composite F is defined, F composite G must be defined. So that is what the problem is. If the range of G is not at all a subset of domain of F, or not at all equal to domain of F, in that case you can't establish that connection from A to C, or from one set to the third set. So in that case, F composite G is not defined. Next, third one, if f is a function from a to a, g is also a function from a to a, same sets involved, then in that case both g composite f and f composite g is defined. This is very clear. If g composite f means g first, f next, there is always a connection because sets are same. A to a, again from a to a. So if both f composite and g composite f are defined, f composite g need not be equal to g composite f. In all the cases, this need not happen. Means composition mapping need not be commutative in all the cases. So these are some observations which are done after defining the composition of two functions. So when you have one function and another function, by combining those two functions we can get a new function, that is called as composition of functions. Now example, let me take the example. If you have functions f and g from R to R, so here codomain and codomain same for both the functions, so both f composite g and g composite f are defined. Therefore no problem of getting not defined. Both are defined as the domain and codomain same in both the functions. F of x is given by cos x, g of x is given by 3x square. So first I have to find out f composite g of x. So f composite g of x is f of g of x, which is equal to f of, what is the value of g of x? That is 3x square. Put it over here, 3x square. Now f of x is cos of x. In the place of x, what you have now? 3x square. That has to be substituted. So cos of 3x squared. So this gives you f composite g. Now if you want to calculate g composite f of x, this is g of f of x. That is g of, what is f of x? F of x entire function is cos x. Okay, so in the place of x now you have cos x. So in the function, right hand side of the function also, 3 into, in the place of x you have to substitute cos x a whole square, which is nothing but 3 cos square x. This is how we calculate composition of functions. So you have two functions. By combining these two functions I got a new function which is cos of 3x square, and another new function is 3 cos square x. Let me consider one more example. This is in the form of arrow diagram. So if you have a function f from a to b and g is a function from b to c, the function is defined like this: 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 5. Then g is taking 3 to 7, 4 to 7, 5 to 11 and 9 to 11. Now I have to define g composite f, which is a function from a to c. Now look at this. The domain range of f is nothing but 3, 4, 5. 3, 4, 5 is the range of f, which is a subset of the domain of g. Domain of g is 3, 4, 5, 9. 3, 4, 5 is clearly contained in the domain of g. Hence, you can define g composite f. Now, see here. 2 goes to 3, 3 goes to 7. So 2 should go to 7 in the under G composite F. So G composite F of 2 goes to 7. So this is acting like a mediator. 2 goes to 3, 3 goes to 7. So 2 goes to 7 under G composite F. Similarly, 3 goes to 4, 4 goes to 7. So G composite F of 3 is 7. 4 is going to 5, 5 is going to 11. So 4 goes to 11 under G composite F. 5 goes to 5, 5 goes to 11. So 5 goes to G composite F of 5 equal to, so 11. This is how we define G composite F. Now in case if you want to define F composite G, you can try that. F first, F composite G means G first, F next. 3, 4, 5, 9, 7, 11, 15. Now here comes the 2, 3, 4, 5. Now that definition is not possible. F composition G is not defined. That is because look here, G first, F next. So this is coming first. Range of G is equal to 7 and 11, which is neither a subset of domain of F nor equal to domain of F. So domain of F equal to 2, 3, 4, 5, whereas range of G equal to 7 and 11. Okay, this range of G is neither subset of domain of F nor equal to domain of F. Hence you can't establish the connection. 3 goes to 7, where that 7 goes to, nowhere you can't establish. There is no connection. Whereas in this case, F is taking A to B, G is taking B to C. There was a connection. Hence, you could define G composite F. F composite G is not defined in this case. That's why I had made a point in the beginning that if G composite F is defined, there is no guarantee that F composite G is also defined. There is a guarantee if domain of G, range of G equal to domain of F or subset of domain of F. Now the third example, one more example. F of x equal to 8x cube g of x equal to x to the power 1 by 3. I have to find out the g composite. In these cases, both are defined because f comma g are functions from R to R. So g of f of x, g of, what is f of x? 8x cube, which you substitute here. Now g of, compare these two functions. In the place of x you have 8x cube. So on the right hand side also, in the place of x you substitute 8x cube to the power 1 by 3. Now 8 can be written as 2 cube, and this is x cube to the power 1 by 3. So a b whole power m, a power m into b power n, like that. So cancel, so you will get 2x. F composite g of x is equal to f of g of x, which is equal to f of g of x is x to the power 1 by 3. Now, which is equal to a, compare these two. In the place of x you have x to the power 1 by 3. So substitute here 8 into x to the power 1 by 3 whole power 3. So 3 cancels, you will get 8x. That is the value of f composite g of x. So the composition of maps is very, very important. That is because we combine two or more functions to get a new function. That also plays a significant role in study of functions. So I hope you understood the concept of composition of functions. Thanks for watching.